So I'm going to talk about the pacemaker cells that are inside the heart and their intrinsic rate and what all of that means. So basically a pacemaker cell isn't a muscle cell, so it's not involved in the contraction, but their activity is what we pick up on the ECG, and we can determine what's happening in the heart by looking at their activity. So they have three key features that I like. So the first one is automaticity. So this means that there's no central nervous system involvement for them to fire. Unlike other electrically excitable cells, they need central nervous system stimuli to actually fire and perform an action potential. These can fire by themselves. They have the ability to be like excitability. So this means that they can respond to stimuli. So if another pacemaker cell sent off a signal by itself, it can talk to the cells next to it, and it can respond to that by sending the signal along the way. Now, to extend on that, they also have conductivity, which means they have the ability to transmit that signal to the other cells. Okay, so what does this mean? So the automaticity, because all of them have that, they all need to have their own intrinsic rate, so they don't all fire at once, because if they did that, then we get dysrhythmias, which we do see, and there's no order, so we don't get a proper heart rate, and it can lead to really lethal dysrhythmias. So basically, a sweet definition of an intrinsic rate is it allows time for others to fire first. So if we look here at our electrical conduction system of the heart, we have the SA node, the AV node, the two bundle branches, and then off of these become the Purkinje fibers. So these all have different rates. So first of all, our SA node usually wants to fire first. So the intrinsic rate of that is our normal expected heart rate, which is 60 to 100 beats a minute. So that's why an SA node intrinsic rate is 60 to 100. Now, if this fails to fire, the next one in line is the AV node. So this is a little bit slower, but not too much. So this one, the intrinsic rate is 40 to 60. Now, the next ones are everything in our ventricles. So these are our bundle branches and Purkinje fibers, and you'll notice that they actually have the same intrinsic rate, which is 30 to 40. So why is this important? Because in our interpretations of ECGs, part of our 5-step method is looking at the rate. Now, by looking at the rate, we can kind of tell and have a guess where the point of origin might be coming from and what type of arrhythmia it might be. So rate helps determine the type of dysrhythmia. So this is a waveform that we would usually see on an ECG. So I'm just going to talk about what we're seeing here compared to what's going on in the heart. So there's two aspects that you need to understand, which is depolarization and repolarization. So depolarization means contraction and repolarization means relaxation. So this is a bit difficult when we're talking about pacemaker cells in contrast to the cardiac muscle cells. So remember that the pacemaker cells will depolarize and they will trigger the cardiac muscle cells around them to contract. So that's why we say contraction is linked to depolarization. Repolarization is when they get all their electrical imbalances sorted out and they are ready to depolarize again. So this is the relaxation phase. So over here I've just drawn our electrical conduction system again, but in relationship to where they are in the heart. So we can see here that the SA node is in the right atrium, and this here is our AV node, and it's kind of like on the border between the atrium and the ventricle. And then we have our bundle branches, which are definitely ventricular, and our Purkinje fibers are ventricular as well. So let's just go over what we're seeing here too. So this is a waveform. We have our P wave, our QRS complex, our ST segment, and our T wave. Oh, and over here is the PR interval. So all of these have meaning, and when we see them change, we need to think, okay, what's going on? Why are they different? And we need to remember this image here about what's going on in the heart and why. So our SA node, which is this red dot up here, should fire first, and it should cause atrial contraction. So the P wave means that's the SA node firing. So if it's upright, regular, rounded, that's a normal SA node depolarization. So we say it's an atrial depolarization, the P wave. Now, from the beginning of the P wave to the beginning of the Q wave, we call this our PR interval. So this is the time between atrial and ventricular contraction or depolarization. So the AV node, the SA node to the AV node. So here, so the time it takes from the signal to go all the way from here to here and then cause the ventricles to contract, because the QRS complex here is actually all the bundle branches contracting and the Purkinje fibers all contracting at once. So that's how we get this massive spike in our waveform here, because the QRS complex is that big contraction. Okay, so we actually have atrial repolarization within the QRS complex too, but we don't actually see it because this is just so big that it covers it up. The next thing is our ST segment. So this will come in handy when identifying MI, so I don't really want to spend too much time on it at the moment. Just know that it is very important. And then this little wave here, which kind of looks like my T wave for some reason, but it's not supposed to. This indicates the ventricle repolarization. So they've had their big contraction, now they need to relax. So this is what this indicates here. So I'm going to talk about what the difference is between leads and electrodes and how they make waveforms either positive or negative and what that actually means. So let's start by what is an electrode. So electrodes are the stickers that we put onto people which connects to the physical wires. They're an electrode. And a lead is the view that those electrodes form with each other. So let's just look at this diagram here. So we have, if we're doing a 3-lead ECG or a 4-lead ECG, we'll have 4 electrodes. These are right arm, left leg, and right leg. So these are just the dots that we put on. So a lead is the connections that they make with each other, which gives us a view, and it will be something that we can see on the ECG. So you'll notice that right leg doesn't actually have a lead connected to any of it, so we call this our grounding electrode. So the most common one we're going to see for a 4-lead ECG is lead 2, which is this connection here between right arm and left leg. And you'll notice that the lead travels in a diagonal direction of the heart. So if we actually bring it over to our heart diagram, this is pretty much the direction of travel for our electrical conduction system. So the SA nodes, the AV, and then the bundle branches. So this is why we like lead 2, because it will give us the most accurate representation of what's going on. Okay, so let's talk through them. So these are called limb leads. So we also have chest leads, which are for 12-lead ECGs, but at the moment I'm just going to talk about these limb leads. So limb leads, we call them bipolar because they are a view between a positive and a negative electrode. So it's between 2 electrodes, that's why they're bipolar. Chest leads are unipolar because they don't connect to another one, they make their own views as well. Okay, so what does this all mean? So let's start off with what's the difference between positive and negative electrodes, and what am I actually looking at, and why do we get this waveform? So we are always going to be looking from the view of the positive electrode. So if we get a electrical induction that's traveling, let's just use lead 2 at the moment. If we get a conduction that is traveling towards left leg, so left leg is our positive electrode in this case, and right arm is our negative. If it's traveling towards it, it's going to give us a positive deflection because it's coming towards us, so it looks bigger, so it's going to go up. If it's going to travel away from the positive electrode, it's going to give us a negative deflection. Because it's traveling away, it's going to look smaller, it's going away, negative deflection. You can also say if it's traveling towards the positive, it's going to give us a positive deflection. If it's traveling towards the negative, it's going to give a negative deflection. Whatever works for you. Okay, so this is why our normal P wave is positive, because it travels down towards this left leg, and that's towards the positive electrode, which will give us a positive deflection. Okay, so let's move on. So what are we going to look at here? So lead 1, between right arm and left arm. The left arm is the positive electrode, so it's going to be looking towards our negative electrode here. So any signals that travel this way will give us a positive deflection. Any signal traveling this way is going to give a negative deflection. Left arm to left leg. So again, left leg is our positive electrode. So any signals traveling this direction will give us a positive deflection, and this direction will give us a negative deflection. So just to recap, lead 1, right arm to left arm. Right arm is negative and left arm is positive, so it's going to be looking from the view of the left arm electrode. Lead 2, which is our standard, is going to be from right arm to left leg. So with left leg being our positive, going to look from the view of the left leg. Lead 3, which is this one here, between left arm and left leg. Left arms are negative, left legs are positive, so it's going to be looking up from the view of the left leg.